Moving on now to Chapter 3. And continuing with functions, we're going to look at them now as tools for modeling situations. We're going to start with polynomial functions. Later we'll expand that to more types of functions besides polynomials. But we are going to increase the degree over what you've worked with in the past. In the past, you were restricted to working with quadratics, at most special cubics. You may not have done anything with cubics. We're going to expand that now to where we're going to let any degree polynomial be a function. Still has to be a polynomial. And remember, a polynomial is an expression where the exponent on x must be a positive integer, or at least a non-negative one. Cannot be a negative integer, cannot be a fraction. Has to be a whole number, has to be greater than or equal to 0. So a polynomial function of degree n means that n is the highest exponent on x. And so a polynomial function of degree n is f of x equals a term with x to the n plus a term with x to the n minus 1 and so forth. So the a sub n is just a number. It's a coefficient. A sub n represents a number. Then x to the n power. A sub n minus 1, x to the n minus 1. This is compact notation using the subscripts to help make it easier to write this. Rather than using A, B, C, D, E, you know, if you had a 50th degree polynomial, you'd run out of letters. But using subscripts like this, you never run out of numbers. So say this was a 5th degree. This would be a sub 5, x to the 5th. But a sub 5 would actually be a real number. It would be a number, not a letter. This is just generally, like we wrote ax squared plus bx plus c, this is the same thing. But now we're going to allow this to go up to any value of n, including a constant down here. So that one doesn't have x in it, but it is still part of the function. So this is the general form. Now we're going to modify that slightly to make it easier to work with. Writing subscripts like this winds up being tedious. If you're working with a general large polynomial function, then it's useful. But we're going to generally be working with small ones. And so I'm going to go back to the A, B, and C terminology just because it's easier to write. This is a polynomial function of degree 2. Our standard quadratic function. We're going to work some with quadratic functions, then we'll go to higher degree. So it's a quadratic function. Looks just like our quadratic equation. Except f might be 0, it might be y. You know, it might be different things, but this is the function where the function definition, we have an input variable of x and an output of f of x. Here's a particular case of that. It's still a quadratic function, but it's been rearranged. We can start from this form of writing a quadratic expression, which is the general form. And by using completing the square, we can rearrange it until it looks like this. The reason that there's some advantage to doing that is this form of writing that quadratic function allows us to very easily find out some information about that function. If you remember, when you draw the graph of a quadratic equation, it's a parabola. parabola has a minimum or a maximum. That minimum or maximum is the vertex. It has an opening direction. Well, in this form of writing the quadratic function, we can read off the location of the vertex without doing any calculation at all. The vertex is located at the coordinates h, k. It opens upward if this is a positive number, down if this is a negative number. So just by looking at that equation, we can get the location of the vertex and the opening direction. That must be a subtraction, though, or in other words, the x value of the location of the vertex is the opposite sign from whatever that is. So if that's a minus, then the x location is positive. If that's a plus, the x location is minus, is a negative. The sign of the y component or y coordinate will be whatever that sign is. HK is the vertex. HK is an ordered pair. This is the x value. This is the y value of the vertex. So that's a parabola. If you're given an equation in this form, you can read off the vertex and the opening direction. If you're given a vertex and a multiplier a, you can write the equation. So there are advantages to having this. Quadratic function plots as a parabola, always. All right, we're going to look at using completing the square to convert this equation, this standard form, into the other form, the vertex form. Because having that vertex has various positives, various pluses associated with it. What we have to do is we have to take this side of the equation and use completing the square to put it in a perfect square trinomial, and then it will have some additional stuff. So let's look at doing that. If you remember completing the square from when we looked at it in circles, you take the coefficient of the x term. In this case it's plus 2. I'm going to take half of that, or I'm going to take 2 and divide it by 2, which gives me 1. I'm going to square that. 1 squared is 1. Well, what I'm going to do is I'm going to add 1 to this, but I'm going to also have to subtract the 1 because I'm going to do everything on the same side. I'm not going to work on two different sides of the equation. I'm going to work everything on the same side. So if I add something, I must subtract the same thing. If I subtract something, I must add the same thing. Add and subtract the same thing on that right-hand side. So I'm going to put that in. I still have the x squared. I still have the 2x. I still have the minus 5. What I've done is I've inserted a plus 1 and a minus 1. That adds up to 0, right? So I've essentially added nothing to that. But what it does for me is these first 3 terms over here now are a perfect square trinomial. And if you remember what a perfect square trinomial is, it's a trinomial or a quadratic that factors into a binomial squared. So I can take these first 3 right here, and they factor into this. X plus 1 times x plus 1. If I combine these, I get the minus 6. So I have that, which if I compare to my vertex form of the quadratic function, compare this to this, it looks the same except for some signs in the numbers. So I can take this number and use the opposite sign, -1. I can take that number and use the sign that's there. That's the location of my vertex. The coefficient in front of this is a +1, therefore that parabola opens upward. That's what it looks like. Vertex, -1, -6, opens up. Remember, through the vertex, you have an axis of symmetry. If you know where that vertex is, that's an important point to actually get an accurate plot of the parabola, so you need that vertex. So once you have it, you also know that axis of symmetry. If you're trying to graph this parabola, because of symmetry, if I calculate a point over here, by symmetry, I automatically have a corresponding point over here. A point over here, I automatically have a corresponding point over here. All I have to do is take the y position and then move, where I move to the right this distance, I move to the left that distance. So this is at -1. So this is 1 unit to the right, this is 1 unit to the left. This is 2 units to the right, this is 2 units to the left, by symmetry. So I really only need to get points on one side of the vertex, and I can automatically have the ones on the other side, by symmetry. It saves how many points you have to calculate if you're trying to graph this. So finding that vertex is very useful. Because we're going to look at something, remember, getting that y-intercept is very easy to do. So, in general, a quadratic function can be written in the vertex form by using completing the square. It's a parabola with a vertex at hk. The vertical line x equals h is the axis of symmetry. The parabola opens up if the constant a is positive. It opens down if the constant a is negative. And remember the transformations we did? If you have this is your base function is the parabola x squared. What we've done is we have shifted it. Remember, when you're inside, it shifts the opposite way of the sign, but it shifts horizontally. We've also shifted it up by k units. The multiplier out here, if that multiplier is greater than 1, we've stretched it away from the x-axis. If it's between 0 and 1, we squeezed it down toward the x-axis. This one is talking about broader or narrower. That we use the vertical rather than the horizontal. Y-intercept is put 0 in for x. If you're starting from this form, that's very easy. If you're starting from this form, you actually have to do a little calculation. But you put x equals 0 and do the calculation. Square h, multiply by a, add k. A couple of other things. If you look back at the original one, up here, a squared plus bx plus c, this comes from the quadratic formula. b squared minus 4ac. If that's greater than 0, that's where your graph crosses the x-axis. Or in other words, the solution to the equation are always where it crosses the x-axis. So if you solve the quadratic equation from the standard form, solve that quadratic equation equals 0, you get x-intercepts. If this is called the discriminant, it's the part underneath the square root. That's the discriminant. If that discriminant is 0, then you have only one answer, and that answer is minus b over 2a. That's where the x-intercept is, and it happens to be the vertex also. If that's less than 0, it doesn't cross the x-axis. Because then you would have imaginary number answers, and you can't have real where it crosses the x-axis are real valued solutions. So if there are no real valued solutions, it does not cross the x-axis. Vertex at h and k. Well, you can get the vertex by doing this, completing the square to go from here to here, but there's an easier way to get there. If you're starting from the general form, ax squared plus bx plus c, you can find the vertex more easily by doing these calculations. The x location is going to be at minus b over 2a. And a and b here A and B are this A and B. So that's where that's the x coordinate of the vertex. Take this value and plug it into the function, and that will give me the y value of the coordinate. So if you do these calculations, this will just be a number. Plug that number into here, and that will give you the number that is the y coordinate. How do you remember that? Quadratic formula, right? Ignore the square root, and that is this equation. The x value is that part of the quadratic. That's how you can remember this. You're supposed to remember this one anyway. So just peel off part of it and just ignore the square root, and that gives you the location, the x location of the vertex. There'll be an axis of symmetry at x equals that number. Remember, an axis is a line, and therefore it must be an equation. It cannot be just a number. It has to be an equation. A vertical line is going to be x equals a number. In this case, it's going to be at x equals h. Whatever this value turns out to be, x equals that number is the axis of symmetry. Oh, okay, I guess I did put that. So that's on the slide. Okay, so here's a function, a quadratic function. So where's the vertex? What's the axis, or which means axis of symmetry? And if you were given that question, you can go about plotting a whole bunch of points and trying to home in on the vertex and the axis of symmetry. But you're never guaranteed of actually getting there. But if you convert to this other form, you're guaranteed of getting there. So we're going to use that instead of the vertex form of the equation, we're going to use that other formula, which just requires that you know A and B. So from the function, we're going to determine what A, B, and C are from here. So these are the values of A, B, and C. The formula is H equals minus B over 2A. So I'm going to plug in B and A, and I get H equals 2. Then I'm going to take 2, and I'm going to plug it back into this function. I'm going to put it in where X is. F of 2 will give me the Y value of the vertex. So I'll put 2 in to my function. That gives me this. If I do that arithmetic, I get 4. So 2 comma 4 is the location of my vertex. The axis of symmetry is X equals 2. No other calculation required once you know where the vertex is. So this is an easier path to follow if all you're asked to do is locate the vertex and determine the axis of symmetry. If you're just asked to find the axis of symmetry, you have to find the vertex to find it. So this is still the easiest way to go. That's when you're starting from a general form of the equation. If you're starting from this form, then you don't have to do any of that. You can just read H and K and set X equals H, and that's your symmetry. So it depends on where you start from as to the path to follow. Unless it's stated that you need to do it a specific way, you're free to pick the one that's the least amount of work. As long as what you're doing is a valid technique, choose the one with the least amount of work, the one that's easiest to do. Okay, so here's a function. Where's the vertex? What's the equation of the axis of symmetry? And we haven't talked much about it, but what's the domain and range of the parabola? If you can remember that from previous class, it should be an easy answer. If not, I'll give you an easy way to do it. But where's the vertex and what's the axis of symmetry? So I'll get those, or did I screw up? Given the standard form, if you're asked to find the vertex, I would use this formula because it's the easiest, the least amount of work. Plug the numbers in, I got H equals 1. Take the 1, substitute it in for X, and gave me 3, which is the Y value. So 1, comma 3, that's the location of the vertex. What's the axis of symmetry? X equals 1. What's the domain of this parabola? Parabola is always negative infinity to positive infinity for the domain. What about the range? To get the range, you have to pick off one other piece of information that was not asked for in this problem. What other piece of information is necessary in order to determine the range? It's there, but you have to recognize it. What else do you need to know to get the range? Y coordinate of what? Okay, you need the y coordinate of the vertex, which we have. But there's another thing you need. Which way does it open? It goes from the vertex up or the vertex down. So knowing the vertex doesn't tell you the range. You have to pick off that other piece of information of which way does it open. Does it open up or does it open down? Which way does this one open? Up, because the 2 is a positive 2, right? And so this range would be from what to what? Yeah, it's going to start at the vertex, the y value of the vertex, which is 3, and it opens up, so it's going to go 3 to positive infinity. Domain of a parabola is always negative infinity to positive infinity. In fact, all of these polynomial functions that we're looking at right now, the domain is negative infinity to positive infinity. Now, you could have a problem limitation, but mathematically it's minus infinity to infinity. But range depends on the function. A parabola is going to have a beginning point or an ending point, but the other one's always infinity. Okay, so how could this be applied in application? Well, an example that comes from physics, but you can visualize as being a situation which could happen. You've all had this experience where you took a ball, threw it in the air, and caught it again, right? Goes up, comes back down. When you throw it, you're throwing it from some height, so that's the starting elevation or the starting value of the height. When it leaves your hand, it has a certain speed. It goes up, stops, comes back down. The height of that ball from the time it leaves your hand until it comes back, if you get the height versus time, that turns out to be a parabola. Because the equation that tells you that is this equation. This is an equation that comes about from doing solving physics, the acceleration, gravity pulling things back down from a certain height and a certain velocity. But this is the equation that results. In this equation, t is time, and it's time in seconds. And s is the height, and that's s in feet. So it's feet and seconds. This says an initial height of 75 feet. That's already been plugged in for you. So you would not be expected to come up with this equation. I'll give you the equation. You need to know how to use it. Just like in this problem. Here's the equation. Where it comes from is some person was standing on top of a building and threw this ball up, and they threw it at a pretty fast speed, 112 feet per second. So it threw it up and it came back down. So S is height, T is time. Time begins when it's released. So that's time 0. how many seconds after you throw it, or after it's thrown, does it reach its maximum height? Well, how would you go about determining maximum? What you have to recognize, this is a quadratic function. T squared, t constant. It's just that it's in t rather than x. But it's a quadratic function. What's the shape of a quadratic function? A parabola. Where is the maximum point of a parabola? The vertex. You know how to find the vertex of a parabola by what we just looked at. So if you're looking for the maximum point on this, you locate the vertex, and that will be the value. How do I know it has a maximum? What does that number right there tell you? It's negative, which means what about the parabola? Opens down. Well, if it opens down, it means it has a maximum, doesn't it? Maximum always occurs at the vertex. So this has a maximum at the vertex. If we locate the vertex of this function, that will give us the maximum height, because in that vertex it has the horizontal variable is time, the vertical variable is height. So the first coordinate will be the time, the second one will be the height. So how many seconds does it reach the maximum height? Locate the t value of the vertex, and that's how many seconds. If we want to know how high it is, get the s value of the vertex. That's the second question. What is that maximum height? Maximum height occurs at the vertex, so use the h equals minus b over 2a formula. Plug the numbers in from that from this equation. Plug those numbers in. H is 3.5. At this point, we could answer that first question, because that's a time. Remember, the horizontal is time, and that's the question to ask. What time? Well, it's 3.5, which means 3.5 seconds. Second question, what's the height? Well, plug 3.5 in for h. You get 271. The maximum height's 271 feet. If you go on to take calculus, you'll actually do this with something called derivatives, and it's really a simple process to find a maximum. But with a parabola, and let me back up. In calculus, you can get a maximum for any function. We're just working with parabolas, and with parabolas, you have this other way to get it, and it works for that. So when you're given a problem of this type, and you're given a function like that, you should notice immediately that it's quadratic, and then remember that there are several things you know about quadratic functions. They're parabolas. They have vertexes. You know how to locate the vertex. The vertex is the minimum or the maximum. It's the parabola is symmetric, and several things of that sort. Things that you can calculate if you have the function. And in a problem of this type, you will be given the function. It'll state it this way. Here's the function, questions based on the function. That's the way the problems will be set up. Okay, here's one using that same information. For what interval of time is the height of the ball greater than 200 feet? What does that phrase greater than imply? What type of mathematics are we going to be looking at if we're doing greater than? Okay, well, that would be true if you were looking at defining a function. But what I'm looking at here now is that implies an inequality. Greater than is that inequality symbol, right? So you're correct if you're defining, plus. So, but now what we're talking about, it means an inequality. And what does greater than 200 feet mean? It means the symbol 200, right? What is it that's greater than 200 feet? The height. Back in this formula, what is the height? Back in this formula, what's the height in here? We've got T and S. One of them's got to be height and one of them's time. Which one's height? S. So S is the height. And so we have height is greater than 200. Well, that doesn't help us much. But we have an equation that says what S of T is. S of T is this. So this has to be greater than 200. Now we have an inequality, a quadratic inequality. So we can solve that quadratic inequality. We do it by solving the quadratic equation. We solve that, and we get these two numbers. Okay, and notice that I'm using T here, not X. T is our horizontal variable. Doesn't matter what the name of the variable is. You still use the same formula for calculating. Minus B plus minus square root of B, so forth. Get two numbers. What do we do with these two numbers? Well, think about what's going on here. You're at 75 feet above the ground. You throw a ball up. It goes up to 271 feet. We just calculated that previously, and comes back down. Question is, what interval time is it greater than 200 feet? Well, it's not 200 when you start, but it does go up above 200, so it has to go above, it has to cross above 200 at some point and then fall back down below it at some point after that. That's what these two numbers are. Those are the times at which it crosses through 200. So what you have is you have a parabola and you have a point. This is 200 feet. So it's the point where it first goes above and the point where it comes back down below. Everything in between, it was above 200. So you take those two numbers as the beginning and ending point of your time, of your interval. So it's actually, you should test it, but you can show that it's true between the points. So it goes from 1.39 to 5.61 seconds. That's when it's greater than 200. When will it hit the ground? Remember, any of these problems, when you're working with ground, you can assume ground is 0. The height is 0. So you plug 0 in for height, which means I have that equation. You solve the quadratic equation, and you again get two values. So what do these two values mean? Negative 0.616 and 7.616. When's it going to hit the ground? Why not the negative 0.616? That's a negative time. You have to throw it out. Mathematically valid, problem invalid. And that's going to be true in many of these things. When you're working with higher degree functions, you might have to throw out some answers because they don't work in your particular problem. They violate the physical characteristics of the problem.